Welcome back. Last episode, we got very good at finding eigenvectors, but only after someone generously handed us an eigenvalue to work with. That leaves a gaping hole. Where do the eigenvalues themselves come from? Today, we fill it. The answer is one of the most elegant moves in linear algebra. We will see that the eigenvalues are exactly the numbers that make a certain matrix singular, and singularity is detected by the determinant. So the eigenvalues are the roots of a single equation, the determinant of A minus lambda times the identity, set equal to 0. Expanding that determinant gives a polynomial whose roots are the eigenvalues. Along the way, we will discover two gorgeous shortcuts hiding in the trace and the determinant of the matrix, learn to tell algebraic multiplicity from geometric multiplicity, and get our first proper look at complex eigenvalues. By the end, you will be able to find the eigenvalues of any 2x2 matrix in under a minute. Let's go. Here is the chain of reasoning, and every link is something we have already proved. Start with the eigenvalue equation, A times V equals lambda times V, and move everything to one side, factoring in the identity matrix as we did last time. We get the matrix A minus lambda times the identity acting on V equals the 0 vector. Now, the crucial requirement, we need a non-zero vector V that satisfies this. When does a square matrix send some non-zero vector to 0? Exactly when that matrix is singular, not invertible, so that its null space contains more than just the origin. So we need A minus lambda I to be singular. And here is the bridge to a number we can actually compute. A matrix is singular if and only if its determinant is 0. Put the links together and you get the headline. Lambda is an eigenvalue of A if and only if the determinant of A minus lambda I equals 0. That single equation is called the characteristic equation, and it is the machine that manufactures eigenvalues. Let's give the star of the show its name. When you expand the determinant of A minus lambda I, you get a polynomial in the variable lambda, and we call it the characteristic polynomial, written P of lambda. 3 facts about it. First, for an n by n matrix, this polynomial has degree exactly n, 1 power of lambda for each row. Second, its roots are precisely the eigenvalues, by the chain of reasoning we just built. Third, over the complex numbers, a degree n polynomial always has exactly n roots, counted with multiplicity. That is the fundamental theorem of algebra, so an n by n matrix always has n eigenvalues if you are willing to allow complex ones. For the 2x2 case, which we will use constantly, the characteristic polynomial has a memorable shape, lambda squared, minus the quantity a plus d times lambda, plus the quantity ad minus bc. Look closely at those two coefficients. The number a plus d is the trace of the matrix, the sum of its diagonal, and ad minus bc is the determinant. The trace and determinant are sitting right there in the polynomial, a clue we are about to cash in. Let's compute eigenvalues from scratch. Take the matrix with 2, 1 on top, and 1, 2 on the bottom. The same matrix we tested last episode. Step 1, form A minus lambda I by subtracting lambda from each diagonal entry. We get 2 minus lambda, 1, 1, 2 minus lambda. Step 2, take its determinant. For a 2x2, that's the product of the diagonal minus the product of the off-diagonal, the quantity 2 minus lambda squared minus 1 times 1. Expand the square, 4 minus 4 lambda plus lambda squared, then minus 1, which gives lambda squared minus 4 lambda plus 3. Step 3, set it equal to 0 and solve. This quadratic factors nicely as lambda minus 1 times lambda minus 3. So the eigenvalues are lambda equals 1 and lambda equals 3. Let's sanity check with the shortcuts we just learned. The sum of the eigenvalues, 1 plus 3, is 4, and the trace of the matrix, 2 plus 2, is also 4. Good. The product, 1 times 3, is 3, and the determinant, 2 times 2 minus 1 times 1, is also 3. Both checks pass. The eigenvalues are 1 and 3. Those two checks were not a coincidence. They are theorems that hold for every square matrix. Here they are in full. The sum of all the eigenvalues, counted with multiplicity, always equals the trace of the matrix, which is just the sum of the entries down the main diagonal. And the product of all the eigenvalues always equals the determinant. These come from Vieta's formulas. The classical relations between the roots of a polynomial and its coefficients apply to the characteristic polynomial. Why should you care? 2 reasons. First, they give you an instant, free check on any eigenvalue computation, add your eigenvalues and confirm you get the trace, multiply them and confirm you get the determinant. If either fails, you made an arithmetic slip. Second, they give deep insight. The product being the determinant means the determinant is 0 exactly when some eigenvalue is 0, which is exactly when the matrix is singular, 3 descriptions of the same fact, finally unified. The trace and the determinant are 2 humble numbers that together pin down the sum and product of the entire spectrum. Let's lay out the whole procedure as a pipeline. On the far left is your starting point, the matrix A. First arrow. Subtract lambda from each entry on the main diagonal. That produces the second box, the matrix A minus lambda I, with those diagonal terms highlighted in gold because they are the only ones that carry the unknown lambda. Second arrow, take the determinant of that matrix. For a 2x2, this gives a quadratic in lambda, the characteristic polynomial drawn here as a parabola. Third arrow, find the roots of that polynomial, which are the places where the parabola crosses the horizontal axis marked by the two red dots. Those crossing points are the eigenvalues, lambda 1 and lambda 2. That is the entire algorithm in one picture: matrix, subtract lambda on the diagonal, take the determinant, find the roots. And the small caption underneath says it plainly: the eigenvalues are simply where the characteristic curve crosses zero. Every eigenvalue problem, no matter how large the matrix, follows this same four-step path. Let's pause and assemble the full recipe, because between this episode and the last, we now have the entire procedure. Given a square matrix A, step 1, form A minus lambda I by subtracting lambda from each diagonal entry. Step 2, compute the determinant of that, which is the characteristic polynomial. Step 3, set the polynomial to 0 and solve for the eigenvalues. That is this episode's contribution. Step 4, for each eigenvalue you found, go back and solve the homogeneous system A minus that eigenvalue times the identity times V equals 0 to get its eigenvectors. That was last episode's contribution, so the order is always eigenvalues first, eigenvectors second. And finish with the sanity checks that catch nearly every mistake, confirm the eigenvalues sum to the trace, confirm they multiply to the determinant, and for good measure plug each eigenvector back into the matrix to verify it really gets scaled by its eigenvalue. 4 steps to find them, 3 checks to trust them. With this recipe you can fully analyze any small matrix by hand. Now an example where something subtle happens. Take the matrix with 5, 1 on top, and 0, 5 on the bottom. Form A minus lambda I and take the determinant. Because the bottom left entry is 0, the determinant is just the product of the diagonal, the quantity 5 minus lambda, squared. Set it to 0, and the only root is lambda equals 5, but notice it appears twice as a squared factor. We say lambda equals 5 has algebraic multiplicity, 2 because it shows up twice as a root of the polynomial. So far, so good. Now let's find its eigenvectors by solving A minus 5 times the identity times V equals 0. Subtracting 5 from the diagonal leaves the matrix 0, 1, 0, 0. Multiplying that by a general vector xy gives y 0, so y must be 0 while x is free. That is just a single independent eigenvector, the x-axis. So although the eigenvalue counted twice algebraically, it only produced one independent eigenvector. We say its geometric multiplicity is 1. The two multiplicities disagree. That example forces us to distinguish two different ways of counting an eigenvalue. The algebraic multiplicity is how many times lambda appears as a root of the characteristic polynomial, a fact about the polynomial. The geometric multiplicity is the dimension of the eigenspace, the number of independent eigenvectors that lambda actually has, a fact about the null space of A minus lambda I. There is always a relationship between them. The geometric multiplicity is at least 1, and at most the algebraic multiplicity. It can never exceed it. When the two are equal for every eigenvalue, the matrix is especially well behaved. It is diagonalizable, which is the subject of next episode, and it means we can find a full basis of eigenvectors. But when the geometric multiplicity is strictly less than the algebraic, as in our 5-5 shear, the matrix is called defective. It is short on eigenvectors, it does not have enough independent eigendirections to fill the space. Defective matrices are the troublemakers of the theory, and recognizing them is exactly knowing when these two multiplicities fail to match. Let's finish the examples by computing the complex eigenvalues we promised last episode. Take the 90-degree rotation with matrix 0, -1 on top and 1, 0 on the bottom. Form A minus lambda. I subtract lambda from the two diagonal zeros and take the determinant. The diagonal product is negative lambda times negative lambda, which is lambda squared, and we subtract the off-diagonal product, -1 times 1, which is -1, so subtracting it adds 1. The characteristic polynomial is lambda squared plus 1. Set it to 0, lambda squared equals -1, so lambda is the square root of -1, that is, lambda equals I and lambda equals -I, the two imaginary units. There are no real eigenvalues at all, which perfectly matches our earlier observation that a rotation leaves no real line fixed. Let's still run our checks, now with complex numbers. The sum, I plus -I, is 0. Matching the trace of 0, the product, I times -I, is 1, matching the determinant of 1. The checks survive in the complex world, and the lesson stands: whenever the eigenvalues come out complex, the matrix is secretly rotating. One more worked example to see a zero eigenvalue in action. Take the matrix with 2, 2 on top and 1, 1 on the bottom. Notice the top row is just twice the bottom row, so the rows are proportional and the determinant is 0. This is a singular matrix. Let's find its eigenvalues. Form a minus lambda I and take the determinant, the quantity 2 minus lambda times 1 minus lambda minus the off-diagonal product 2 times 1. Expanding the first product gives 2 minus 3 lambda plus lambda squared, then subtract 2, leaving lambda squared minus 3 lambda. Factor out a lambda, lambda times the quantity lambda minus 3. So the eigenvalues are lambda equals 0 and lambda equals 3. The 0 eigenvalue is not an accident. It appears precisely because the matrix is singular. A 0 eigenvalue means there is a non-zero vector the matrix sends to the origin, and its eigenspace is exactly the null space we studied earlier in the course. Run the checks, the eigenvalues sum to 3, matching the trace of 2 plus 1, and they multiply to 0, matching the determinant. Singular matrix, 0 eigenvalue, two faces of the same fact. This figure makes the trace and determinant shortcuts visible. We are looking at the characteristic parabola for a 2x2 matrix, lambda squared minus the trace times lambda plus the determinant. It opens upward and crosses the horizontal lambda axis at 2 points, marked in red. Those crossings are the two eigenvalues. Now watch where the trace and determinant live in this picture. The sum of the two roots equals the trace, and geometrically the sum is twice the location of the parabolic axis of symmetry, so the midpoint between the two crossings, marked with a gold tick, sits at half the trace. The trace controls where the roots are centered. The determinant equals the product of the two roots, and for this parabola the product of the roots is exactly the y-intercept, the height at which the curve crosses the vertical axis, marked with a teal dot. So one number, the trace, fixes where the eigenvalues are centered, and the other, the determinant, fixes their product. Slide the trace and the roots shift together, raise the determinant, and the roots pull apart or even leave the real line into the complex plane. Let's step back and read the roots like a diagnostician. The kind of roots the characteristic polynomial has tells you the geometric character of the matrix. If you get two distinct real roots, as with our 2, 1, 1, 2 matrix, the matrix has two genuine stretch axes and is diagonalizable. If you get a repeated real root, the matrix might be defective. You have to check whether the eigenspace is big enough, as we did with the shear. And if you get a complex conjugate pair, of the form a plus bi and a minus bi, the matrix is performing a rotation, combined with a scaling by the magnitude of that complex number, the square root of a squared plus b squared. One important guarantee for a matrix of real numbers, complex eigenvalues always come in conjugate pairs. One, the mirror image of the other across the real axis. That is forced by the fact that the characteristic polynomial has real coefficients. We will devote a full later episode to what these complex eigenvalues mean and how to extract the rotation angle. For now, treat the appearance of complex roots as a flag that says, rotation lives here. A little history to close. The characteristic equation itself goes back to Augustin Louis Cauchy in the 1820s, who introduced it while studying symmetric systems that arise in mechanics and in the astronomy of planetary orbits. He needed the special values that govern how such systems oscillate. In the 1850s, Arthur Cayley and William Rowan Hamilton discovered a remarkable fact now called the Cayley-Hamilton theorem. Every square matrix satisfies its own characteristic polynomial. If you plug the matrix itself into its characteristic polynomial, you get the zero matrix, a deep and useful identity. In the 1870s, Ferdinand Frobenius built the rigorous theory of the characteristic and minimal polynomials that we still teach. And the word eigen, as we saw last time, came from David Hilbert around 1904, German for own or characteristic. That older English word characteristic survives in the name characteristic polynomial, and it is well chosen. This one polynomial truly does characterize the matrix, encoding its entire spectrum of eigenvalues. Let's recap. The key idea, lambda, is an eigenvalue exactly when a minus lambda times the identity is singular, which happens exactly when the determinant of a minus lambda I is 0. That is the characteristic equation. Expanding the determinant gives the characteristic polynomial of degree equal to the size of the matrix, and its roots are the eigenvalues. Two shortcuts hold for every matrix: the sum of the eigenvalues equals the trace, the sum down the diagonal, and the product of the eigenvalues equals the determinant, both perfect for checking your work. We distinguished algebraic multiplicity, how many times an eigenvalue is a root, from geometric multiplicity, how many independent eigenvectors it has, with the geometric never exceeding the algebraic. When geometric falls short, the matrix is defective. And complex roots, which always come in conjugate pairs for a real matrix, signal that the matrix is rotating. Next episode, we finally put eigenvalues and eigenvectors together to diagonalize a matrix, rewriting it in its own natural basis, where it becomes nothing more than a clean list of stretch factors. Today we found where eigenvalues come from. The key insight is that lambda is an eigenvalue exactly when the matrix A minus lambda times the identity is not invertible, because only a singular matrix sends non-zero vectors to 0, and a matrix is singular precisely when its determinant is 0. So the eigenvalues are the solutions of the characteristic equation, the determinant of A minus lambda I equals 0. Expanding that determinant produces the characteristic polynomial, a polynomial in lambda whose degree equals the size of the matrix and whose roots are the eigenvalues. We found two beautiful shortcuts that hold for every square matrix. The sum of the eigenvalues equals the trace, the sum of the entries down the main diagonal, and the product of the eigenvalues equals the determinant. We separated algebraic multiplicity, how many times an eigenvalue repeats as a root of the polynomial, from geometric multiplicity, the number of independent eigenvectors it has, and saw that the two can differ. And we previewed complex roots, which signal that the matrix is secretly performing a rotation. Next episode, we put eigenvalues and eigenvectors together to diagonalize a matrix, to rewrite it in its own natural basis, where it acts as nothing more than a list of stretches. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.